Good afternoon, everyone, and welcome to MOS Live Virtual Planetarium. In just a few moments, we'll be meeting our educators who will be taking us on a tour of exploring space today. My name is Christina. I'll be serving as your moderator today, and although you can see my face now, you'll mostly be hearing my voice in the background as I share your questions and observations and comments with our educators. And if you'd like to ask a question or share an observation or answer one of their questions to you today, and you're watching us on Zoom, you can do so by clicking on the Q&A button at the bottom of your screen. Don't forget to include your name and age if you would like a shout out. If you need captions today, you can get those by selecting closed captions and then showing captions on the bottom of your screen as well. If you happen to be watching on Facebook or on YouTube today, unfortunately, we will not be able to see your questions or observations, but we're really happy you're here joining us for the show, and we hope you do enjoy it. But with all of that being said, I'd like to invite our educators to turn on their cameras, introduce themselves, and get us started.
Thanks, Christina. Hi, everybody. My name is Katie. My pronouns are she and her, and today I will be your guide as we explore space. So I will be doing most of the talking, but I can't do it alone.
Hi, everybody. My name is Talia. I also use she, her pronouns, and I am going to be your pilot today, flying us through space.
Awesome. So I thought today it would be fun to talk about stars, specifically how they form, and then how they quote unquote live, and then when they run out of fuel, how they die. And the first place that I wanted to stop on our journey today is the sun, because we live very close to the sun. It's the closest star. It's about 93 million miles away, and we are orbiting around it. It's the only star in our solar system, but because we're so close to it, much, much closer than other stars that we see in the nighttime sky, we can study it, and we can use a lot of the information that we know about our star to study other ones. So right now, Talia has us nice up and close near the sun. So if you were looking at this in real life, you would probably damage your eyes quite a bit. And also you wouldn't want to be this close if you were out traveling in space. So do be careful if you're ever trying to observe the sun. Make sure you have the proper filters or glasses in order to safely observe. All right, so we're getting up close now. So does anybody know what stars or the sun is made of? And you can go ahead and type that into the Q&A. If you know, or if you don't know, you can also just put a question mark or say, I don't know, because that's totally fine too.
Awesome. We're going to give our folks a moment to type in their responses, Katie. I know I'm not the fastest typer myself, but we have some ideas coming in now. So it looks like the darlings think that it might be made out of gas and plasma. It looks like Max, age 11, was also, or he just had an oops moment, actually. Never mind there. We have guesses for gas, a couple of question marks, and one more gas.
Awesome. Yeah. So I like both gas and plasma because it's kind of both. So there are three states of matter, right? We have solid, liquid, and gas. And then there is another state of matter called plasma. And so basically, if you take gas and you heat it, you energize it a lot, it turns into this material called plasma. So that's basically what the sun is. It's super heated, super energized gas that is plasma, essentially. So it kind of acts like a fluid in some ways when we observe like the rotation of the sun and things like that. But the actual elements that make up this plasma are hydrogen and helium. And we know that all of the stars in the universe are composed of primarily hydrogen and helium. And this was a discovery by Cecilia Payne in the kind of early 1920s. She was the first person to discover that stars were actually made of these elements as opposed to the same elements that the Earth is made of. And so since then, we've been able to kind of track the lives of stars and figure out their age and, more than just their composition, but how hot they are, their brightness, things like that have come a long way in the past century. So our sun is a fairly average star. as far as stars come. It's not super huge. It's not super tiny either. To kind of put it into perspective, if you were to open it up like a cookie jar and try to fill it with Earths, you could fit about 1 million Earths inside of the sun. So it is pretty massive comparatively, but it's an average star, average in temperature, average in brightness. So just kind of a standard run-of-the-mill star. And a lot of our observations of our own sun have helped observations with other ones. So we use telescopes such as the Solar Dynamics Observatory, which is an observatory that's in orbit around the Earth, and it studies the sun in all different types of light. So not only does the sun emit visible light, or light that we can see, but it also emits light across the entire electromagnetic spectrum. So wavelengths that we can't see with our own eyes. So we can use telescopes to perceive those other wavelengths. Another space telescope that is studying the sun is called the Parker Solar Probe, which was a fairly recent spacecraft to launch and then head into orbit around the sun. And it's making the closest pass of any space probe ever to the sun. So that's going to study things like, why is the atmosphere of the sun so hot? It's much, much hotter than kind of the surface region. So it's going to uncover some mysteries about our sun, which is really exciting. Now, to study other stars, we also use telescopes such as the Hubble Space Telescope. You might have heard of that one, or the Chandra X-ray Telescope. And so these telescopes, their primary purpose is to look really, really far out into the universe. So to galaxy or stars in our own galaxy, but also other galaxies as well, and try to get some idea of how galaxies form and how the universe is structured and things like that. So these telescopes primarily focus on things that are much farther away. On that note, I think that we should also get a little bit farther away, because we have that ability using this program, which is called OpenSpace. It is a free program that you can download at openspaceproject.com. We'll have that link listed at the end of the program for you today. It is very taxing on your computer, so you got to make sure you got a lot of space and the ability to run it, but it is really cool. It's kind of similar to the software that we would use in the actual Planetarium theater. All right, so we are leaving our solar system behind. That blue orbit line right there that you can see is the orbit of Neptune. And then we've still got a couple of other areas past Neptune that are still inside the solar system. So places like the Kuiper Belt and the Oort cloud. But we're gonna go out even farther than that. We're gonna go into interstellar space. And if you have ever looked up at the nighttime sky before, you've probably recognized a lot of stars, or maybe, just connected some lines for the constellation. So we can throw those up there as well. And you'll see that a lot of them are actually still pretty intact. Like there's Ursa Major in blue over on the right side of the screen. I saw Leo just a moment ago. So even though it looks like we're really far away from the solar system right now, we're actually not that far compared to the other stars, because the constellations are still intact. So we can go a little bit further and you can see how those constellation lines change. So we're kind of on the order of many light years away from the solar system now. A light year is roughly 6 trillion miles, just for comparison. I know it sounds like a time, but a light year is the distance that light travels in a year. So like I said, 6 trillion miles. And at this point, we are probably hundreds of light years away from the solar system, which we would never be able to send anything all the way out here at current technologies. It would take way too long. So that's why we do use telescopes, like I mentioned earlier, the Hubble and the Chandra and Spitzer and a whole bunch of others, to study the light from these stars from rather close to home. All right, so now the constellations kind of look all out of whack, right? Because we're viewing them from a different perspective inside of our galaxy. So they're not super helpful anymore, although you will notice that they kind of all look like they converge at one point, which would be our solar system, because the constellations were made from the perspective of the Earth. So that's why they look all wonky now that we have changed our perspective. So we'll get rid of those and we can float in space for just a moment. before we start diving into the life cycles of stars. So we mentioned earlier that stars are made of hydrogen and helium, but where does all of that hydrogen and helium come from? Like, how do stars actually form into giant balls of this really hot energized gas called plasma? Well, there are these objects in space called nebulas. Now, does anybody here know what a nebula is? And if you do know, you can type in what you think it is, or if you don't know, that's totally fine too. I'm going to show you a lot of different types of nebulas in just a moment. Also, if anyone has had any questions so far, I'm happy to take some questions as well.
Sure, thanks, Katie. Well, maybe while the answers are slowly coming in, we had two questions about the sun. I'm assuming our sun in terms of this our solar system. And the two questions were, I guess, like why we only have one sun in our solar system and what are sunspots?
Ooh, both very good questions. So why do we only have one star in our solar system? That is a really good question. I'm not sure that I have the right answer for it, but it all has to do with when the sun formed. So stars come from these giant clouds of gas and dust. And so if there aren't a ton of stars forming in this giant cloud, then our sun might have been really far away from another star, and over time they kind of migrate away from each other. So it's just possible that our sun didn't really have any super close siblings, for lack of a better term. But there are actually a lot of stars out there that are part of binary systems. So there are 2 or 3 or even 4, sometimes more than that, that are part of a system. So they're kind of all gravitationally bound to each other and they can orbit each other. So actually a lot of the stars that you see in the nighttime sky, while they might look like individual stars, a lot of the times they're actually binary systems, or at least 2 stars that are orbiting around each other. But they're so far away that you can't tell that there's 2 stars there. It just kind of looks like one pinpoint of light. As far as sunspots go, another great question. So when we were looking at the sun, you might have noticed that there are some darker areas on the surface, and those areas are slightly cooler than the rest of the surface of the sun, or any star can have sunspots. And it has to do with the magnetic field of the sun that creates those kind of slightly cooler pockets on the surface. And they do kind of migrate around and come and go depending on how active the sun is at the time.
Awesome. Thank you, Katie. That's really helpful. And that did give our viewers a chance to type their responses too. So in response to what is a nebula, Asher and Nora said gas. Maybe they think they actually already saw one. Lily says a bunch of dust. Isora says an exploded star, maybe. Emma Layton says maybe a nebula is a galaxy. And maybe also a star or made up of lots of stars. And last one here is a group of stars, dust, and gases.
That is awesome. Pretty much all of those answers are correct because there are so many different types of nebulas out there. But to give you the most general definition, they are giant clouds of gas and dust in space. And generally they are within galaxies. So an entire galaxy itself wouldn't be considered a nebula, but galaxies contain many nebulas, and they can also form after a star has died. So any kind of star can create a nebula after it has run out of fuel. And stars also come from nebulas, from these giant clouds of gas and dust. So I am now going to switch over to some visuals on my end and show you what a stellar nursery looks like. So this is called a star birthing nebula. And it's basically a cloud of gas and dust that is perfect for star formation. So these types of nebulas specifically tend to be cold and very dense. So material can clump together pretty easily, and over time attract more and more material, because anything that has mass or is made up of stuff also has gravity. And gravity, the more massive something is, the more gravitational attraction something has. So kind of as these clumps get bigger, they just keep attracting more material over and over and over until the clump gets so massive that it collapses under its own gravity. And so when it collapses, we get pressures and temperatures skyrocketing in the core, and that is what ignites a star. So you have lots of high temperatures and pressures that cause material to smash together and form into new material. So like hydrogen smashing together to create helium. This process is called nuclear fusion, and that is what is fueling a star throughout its life. So it's converting hydrogen into helium. And you'll see in this nebula, there are lots and lots of stars being formed, lots of baby stars. And there's still a lot of material around these new stars. So right here, you're looking at what's called a protoplanetary disk, or a proplid for short. And it's essentially a baby solar system. So you have the new star in the middle, and then that material surrounding the new star will eventually kind of clump together and form things like planets and moons and asteroids and anything else that you might find in a solar system. So the sun started out in something like this, but because our sun is 4.5 billion years old, it's about halfway through its life. It has kind of blown away all of that extra material around it. So we don't see a nebula surrounding our sun anymore because our sun is just simply too old at this point. And I'll leave this going for a moment. Does anybody have any questions about star birthing nebulas or how stars form?
We do have a couple of questions, Katie. I think one is specifically about the colors we're seeing. And I guess why are we seeing these different colors that you might see in a nebula or something like a galaxy?
Yeah, that's a great question. So there are nebulas in general are usually very colorful because of the gases that they're made up of. So mostly hydrogen and helium gases are present within nebulas, but there are other elements as well. So different colors come from different gases, but also a lot of the images that you may have seen from nebulas or other galaxies have been colorized to signify different things about the image. So sometimes if you've seen, like a picture of a nebula that's got a lot of red and it also has a lot of blue in it, sometimes those colors will indicate whether, there's a certain part of it that's really hot or a certain part that's cooler. So sometimes the different colors that you're seeing from images are there because they indicate something about the image. And then other times it's just the natural colors of the object viewed in visible light. So they are very colorful, but sometimes it's not always the same colors that you are looking at.
Awesome.
All right.
We did have one more question, if you don't
Sure.
mind, Katie, about
Absolutely.
the shape, because there's a couple of people who wanted to know, why does it get shaped like a disc?
Yeah, another really good question. So if you've ever seen, like when we were looking at our solar system, right, everything was kind of orbiting in the same plane. Like if we saw the solar system from the side, you might have noticed that it's very thin. Or if you've looked at Saturn's rings, that's very thin. Or some galaxies, spiral galaxies also look thin. And, protoplanetary disks or baby solar systems also are in a disk shape. And that all has to do with something called angular momentum. So everything is pretty much spinning in space, and that spinning motion causes everything to flatten out. So, gas, dust, material, planets, galaxies, stars, as long as they're spinning, they tend to flatten out over time. It's a very strange phenomenon, but it is very prevalent throughout the universe. All right, so that's our first nebula today. Now, the second type of nebula I'm going to show you is a nebula that happens after a very average star runs out of fuel. So our sun, as I mentioned, is an average star. So not all stars, explode at the end of their lives. Most average stars tend to just get really big and they puff up, and so they become less dense. and they get really, really big, and then eventually they just shed their outer layers of gas. And so they form these beautiful ring-like nebulas, where you can see there's different colors, which again are different gases. And then right at the center there is the remaining core of the star that once existed all together. So that core is called a white dwarf. And it, again, is just the really dense, hot, leftover material in the core of the star. And the rest of it, all those layers that you can see, are the outer layers of the star that have been shed away. And this is a generally, I guess, when it comes to events in space, a more gentle process, where it's just kind of puffing up and floating outward rather than a big explosion. And this is called a planetary nebula, which I know that's a kind of a weird term because it really doesn't have anything to do with planets. But I think that when they were first discovered, a lot of astronomers thought that they might be planets because they were so colorful and they looked a little bit like planets through a telescope. So the name just stuck. And so now that's what we call these nebulas after an average star dies, planetary nebulas. All right, so that is what will eventually happen to our sun, but not for another 4.5 billion years. So you don't have to worry about canceling your weekend plans or anything like that, at least on the sun's behalf. But if you are an incredibly massive star and you're running out of fuel, so something like a red giant or a blue giant star, once you start to run out of fuel, there is an initial collapse. So basically the star can't hold itself up anymore. So it collapses in on itself and then bounces back off the core in this really massive explosion. And I don't think I've said the word yet, so I'm going to throw it out to our audience today. Does anybody know what it's called when a really massive star explodes? It's possible I gave it away, but that's okay.
Well, it's perfect timing, Katie, because we definitely had a question from Max already about how are these supernovas formed, and a lot of supernovas coming into the chat right now. Perfect.
Yeah, so this is exactly how a supernova happens. This is an animation, of course, but it's essentially a really massive star collapsing in on itself and then bouncing off the core and exploding out into space. So all of this material is speeding through space at a large fraction of the speed of light, and it's forming another type of nebula called a supernova remnant. And so again, lots of beautiful colors, gases, just a different way that this nebula was actually formed. So this star right here is a blue giant, but there are other types of stars that can go supernova as well. Now, what's really awesome, I think, about supernovas is that the energy created when the star explodes, or I shouldn't say created, but the energy released during a supernova explosion actually creates new elements, heavier elements than could be made inside of a star. And so all of the material around us, everything that's in our bodies, literally came from an exploding star at some point in history. So we are quite literally made of star stuff, which I think is pretty awesome. All right, so then after a supernova happens, the core of the star will continue to condense down. And depending on how big the core is, it can turn into a couple of different objects. It can turn into something called a pulsar, or it can turn into a black hole. So black holes are essentially a whole bunch of mass, a whole bunch of material from the core of that star that collapses into a teeny, teeny, tiny point. And so I'm going to switch over to a black hole animation really quick. So this is, again, an artist's rendition, and this was taken from the European Space Observatory, or excuse me, the European Southern Observatory. And this is just an artist's rendition. But basically, you have all of this mass in an infinitely small point. And it seems like physics kind of breaks down at this point, which is called the singularity. But we can see the effects of black holes because they have a very strong gravitational attraction. So they can pull in, if a star or a giant cloud of gas and dust is too close to a black hole, it can fall into it. And so what you're seeing now, or just a moment ago, was a star that was slowly kind of getting pulled in and is accreted around the black hole. So basically that material is just orbiting around and spiraling into the black hole. That's what accreting means. And it's heating up on the way in because of friction and the gravitational forces. So you can see a whole disk. Again, we see the disk shape. There it is once more. And then there's lots of energy released from either side. So I will pause there and see if there are any questions.
That video was super cool, Katie. It's my first time seeing it, and I think the viewers enjoyed it too.
Awesome.
But we had two questions kind of related to a star age and supernovas. So I guess the questions are basically, how long does it take for a star to explode, if it's an example like the one you mentioned, but also how old do stars typically get?
Yeah, that's a great question. So the actual explosion part happens in like a fraction of a second. It's very, very quick. But that material that's then traveling through space, I mean, that's just going to keep going. There's nothing really there to stop it. So the nebula that forms after a supernova will just continue getting bigger pretty much forever until the material is so far away that it doesn't look like a nebula anymore. And then in terms of the ages of stars, so it really depends on what type of star it is. So our sun is an average star, and it will live for a total of about 10 billion years. And that's generally what we see across most average stars. Very low mass stars, so those are the smaller ones, something like a red dwarf, those can live for trillions of years. And the universe is about 13.7 billion years old. So that means that we've actually never seen a low mass star die because they're so fuel efficient that they're all still going. They haven't had enough time yet to actually run out of fuel. They're very, very efficient. Very massive stars, so stars that would go supernova, those stars probably only live for tens of millions to hundreds of millions of years on the longer end, which I know still sounds like a long time, but it's really not that long compared to average or low mass stars.
Awesome. Thank you, Katie. And I'm just going to pop back in because I just looked at the time and it looks like that may have been the last question we have time for. So I want to thank Katie and Talia for running us through that show today. It was really cool. Thank you to you both. You can say goodbye to the audience.
Bye, everyone. Thank you.
And I want to thank everyone who joined us today for the program. You all had some wonderful questions and observations. And if we weren't able to get to your question today, I do apologize. We only have so much time. But what I can say is we're going to do more shows like this and other topics throughout the weeks. So if you would like to see more of our offerings, I would definitely encourage you to visit our website at www.mos.org/mos@home. Also, if you'd like to figure out how you might be able to support the museum in doing programs like these, you can visit our website at engage.mos.org/welcome. And if you would like to try out the software that we use today to kind of take this tour of space in general, not just our solar system, you can check out OpenSpace at openspaceproject.com. Thank you all for joining the program today, and we will catch you at the next one.